Good morning. Good morning. Let us start today's lecture. So relatively today's lecture is a bit simple. It's just simple and we don't cover that much. It is only 2 or 3 topics. But before we start today's lecture, let's go back to what we did last week. A little bit spending on last week before we start our lecture. So, if you remember, let's talk about sampling distribution of the mean. But before we talk about sampling distribution of the mean, let us talk about this one. There is a population, let's say students enrolled in Econ 7300. So this is the population, all students enrolled in Econ 7300 in semester 2, 2019. So suppose the heights of students are normally distributed with mean 168 centimeter and the standard deviation of 8 centimeter. Assume this information is given. Now I am picking one student. I pick randomly one student and I am asking a question. What is the probability of randomly selecting a student from this population who is shorter than 160 centimeter? It is the same thing, for instance, you do mid-semester exam. Now you all have a mid-semester exam result. What is the question that you are asking? What is the average mark? What is the standard deviation? That is the question that you would ask so that you would know where you are. If you did a mid-semester exam and I release your results, the question you would ask me, what is the average mark of all students and what is the standard deviation? So let us assume that the standard deviation and the population mean of height is given. So keep in mind that I am picking only one student. I randomly pick one student, and that student is 160 centimeter. So I want to know what is the probability less or equal to 160, or I could also greater or equal to 160 centimeter. So in this case, because I am only picking one student from the population, we have to apply this formula. This is X only for the student that randomly selected student. 160 minus 168 divided by the population standard deviation. I get minus 1. The question is asked less than, shorter than 160 centimeter. I go and find 15.87. So this is what we did before. So this is the X scale. This is the mean, 168, and this is 160. This is the X scale. I converted X scale to Z. So what is the value here? Z value. What is the value of Z here at the center? Z would be equal to? Who will tell me Z at the center? Z equal to? 0. So this is what I want to know, less than 160. Z, so the Z scale, Z is 0. I converted to minus 1. I want to know the population. So I have to go to the table and find less than 1. So I went to the table to find this probability, which is 15.87. If I want to find minus 1, I go to the table, I search for minus 1, and it gives me 15.87. So that is fine. Now let us talk about samples. This is the population. I take one sample. There is so many samples. If I say the sample height of this student is 160, what question would you ask me? Are you asking, for instance, if I tell you this is the students, I gave the height, I measure the height of the student, I pick randomly one student, and then the question that you would definitely, the same thing when you get your exam result, the question that you would ask, what is the average of all students' result? What is the standard deviation? What about now if I am talking about sample? I take a sample mean. A sample mean, there are so many sample means. If the sample mean is 160, what is the question that you would ask? Are you asking for the population mean or for the sample mean? So you would ask, because we are now talking, you would ask what is the distribution of the sample, not the distribution of the population. If I pick one student in your exam result, the question that you would definitely ask me, what is the distribution of the whole students, because I am picking one from the students. Now it is sample. When I take a sample, the question that you would ask, what is the distribution of the sample? How does the other samples look like? My sample, okay, it is saying 160. What about the other? That's why we need a sampling distribution. So, the sampling distribution, so whenever a single score is this one. Whenever a single score is taking, selected from a population, you need information about population mean and population standard deviation. Use that information in order to get Z value. Once you get Z value, you go to the table, you tell me the probability. That's what we did. Well, but most of the time, we don't pick one student, we take a sample. So you never find in any study that you ask only one student. You have to take a sample. In that case, we are no longer using X. We have to use X bar because we are talking about the sample. Now the question is that, what information is required if instead of a single score, you are using a sample mean? For a single score, you ask the distribution of the population mean and population standard deviation. For a sample mean, your question has to be, first of all, we are not going to use this formula. At least we have to change this one to X bar because we are talking about samples. So instead of X, we should use X bar. And also we need to know what is the distribution of the sample mean. Because there are so many samples. So you would like to know what is the distribution of all these samples. Keep in mind, when we are doing these things about this question, we don't know about the population mean. We are assuming we know that the population standard deviation, but we don't know the population mean. It is difficult to know the population mean. All students at UK, what is the average age? You have to ask everybody in order to know. But most of the time, it is difficult to know. So let us assume the population mean is difficult to know, but we are assuming we know the population standard deviation, but we don't know the population mean. Now we are using a little bit trick to know what the population mean would be. So anyway, go back to that. If it is a single score, you want to know the distribution of population mean, population standard deviation. If you are talking about means, sample mean, you need to know about the distribution of the sample mean because you are talking about sample. This sample, this sample, this sample, this sample. The question that you have to ask, if your mean result is 10, then the question that you would ask, what about the other students, the other group of students' result? So 1 group, 2 groups, 3 group, 4 group, 5 group. One group gets a result of 5. This group would ask me, what about the other groups? What do they get? But if I ask you all students one question, and then I tell you this is your result, the question you would ask me, what is the average of the whole students? So when you are talking about the group, you would ask about the other groups, definitely. If I give you a group assignment, when I give you your result, you would ask me, what about the other group? What did they get? Because we are talking about the group. Okay, so definitely we don't use this one. So let us try to know what this and this. We did that last time, and we arrived to this one. The mean of all possible sample means of size n is equal to the population mean. Keep in mind, we don't know the population mean, but we could know if we take several samples and we take the mean of each sample and we add them and take another sample. So the mean of all sample means would be equal. So there is a mean here, another mean, another mean, another mean, another mean. If I add all the means and make another mean, that would be equal to the population mean. So we don't know the population mean, but at least through this one, we would guess what the population mean would be. What about the population standard deviation? So this one would be equal to this one. This is the mean of all population sample, the mean of all sample means. The standard deviation is no longer sigma. The standard deviation is no longer sigma. The standard deviation would be the population standard deviation divided by the square root of the sample size. So finally, the formula has to be like this. When we are talking about sample, the formula has to be like this. Keep in mind, we don't know the population mean because it is difficult, but we are assuming that we know the population standard deviation. We are assuming we know the population standard deviation. So let's go. So there is also central limit theorem. What is saying that if the population is normal, regardless of shape, if we have at least 30 sample size, that would be fine. We don't need to worry. A sample size of 30, for instance, this distribution, the age of the distribution of these students might not be normal. For instance, if I take all age, maybe the age might not be a bell-shaped. Maybe it's a little bit to the right, or maybe it would be a little bit to the left. But if I take a sample of 30 from many sample of 30s, then that distribution, the distribution of each sample mean, could be looking a normal distribution. The second one, if the population is normally distributed, we don't need to worry about the sample size. Okay, so let's go to one example. Keep in mind, we don't know the population mean. What we know is the population standard deviation. But we have some idea here. The mean of all possible sample means of size n is equal to the population mean. So we are taking one sample. By taking one sample, we could still talk about this one. Okay. Let's take one. A manager of a well-known pizza shop claims, because he doesn't know the population mean, but he could claims that the average home delivery time for their pizza is 30 minutes. And then let us assume you want to open the pizza shop and you want to, to test whether what this person is saying is really correct or not. Because he is claiming that 30 minutes we will give you your pizza once you ordered. Let's say you want to open your own pizza shop and you want to test whether this 30 minutes is really correct or not. So a random sample of 40 home delivery pizzas was collected and the sample mean was found to be 33. Do you have a case against the manager's claim? What would you say about the manager? What he said 30 minutes. What would you say about that? We don't know the population mean. He is claiming, but we know the population. So assume the population standard deviation is 6.5, which means we know the population standard deviation, but we don't know the population mean. He is just simply claiming. Okay, now there are two cases. Here you have one of the two decisions. One, the sample result, 33 minutes, is not unusual. You would say that it could happen, 33 minutes could happen. If I take a sample, he said 30, 33 could happen. Such a sample result, 33 minutes, is likely to occur. One thing that you would say, it would likely to occur. So probably what he is claiming is correct. The second thing that you would say, if he is saying 30, why do I get 33 when I take a sample? This is really unlikely. It is unusual. I shouldn't get 33 if what he is saying is correct. If what he is claiming is correct, you are doubting your result. Why do I get 33 minutes? So this is unusual. It is unlikely. Unlikely means less probability. Likely, high probability. Let us now, these are the two options that you have. Either to accept the claim or to refute the claim. So, in our example, 33 is greater than 30. The manager said 30. You found from your sample 33. 33 is greater than 30. So let us try to find the probability 33 or above. In our example, the sample result 33 minutes is high. So high means high than 30. It is high. So what is the probability of getting a sample result this high or higher? So I did all the things. This is X bar scale. This is 30. This is 0. This is 33. When I calculate, I found 2.92. Then the probability, I go to the table. The probability to the right of 2.92 is 0.0018. So this is really unlikely. So I shouldn't get this one. If what he is saying is really correct, if this 30 is really correct, I shouldn't get these things when I take a sample. That is what you are saying. But you get that result because you take a sample. So what does it mean? What does it mean? Maybe the manager is understating. The manager is not telling me the truth. Maybe it takes 32 minutes. Maybe 32.5. So he didn't tell me the truth because the probability is here very low. So there is less than 1% probability of getting a sample result this high or higher. Such a sample result is unlikely to occur. If what he is saying is correct, the probability that I would get this one is very small. I shouldn't get this 33 if what he is claiming is true. If what the manager is saying 30 minutes is true, I shouldn't get this 33 minutes. Such a sample result is unlikely to occur if the population mean is actually 30 minutes. Because he is claiming, you want to test his claim. Sometimes, a manager would say, that a university would say that, once you graduate, you will get 60,000 in a year. Then you doubt about that claim. You take a sample of students who graduate, and then you make this analysis, and then whether it is likely or unlikely, whether the claim is correct or not correct. In this case, it is unlikely that these things to happen, but it happened. My data tells me 33. Such a sample result is unlikely to occur if what the person tells me is correct. But because it did occur, means my sample tells me this one, but because it did occur, we have evidence that the population mean is not 30 minutes. The claim is not correct. He is understating. He is not telling me the truth. He said 30 minutes, but probably it could be 32 minutes. Probably it could be 32.5. Probably it could be 33. So you don't accept his claim. You doubt the claim. He didn't tell the truth. Because we don't know the population mean. That's what we are going to do in this lecture today. Today also, we don't know the population mean. But we could gauge the population mean using a confidence interval. That is what we are going to do. So, you see, the sampling distribution is really important. The whole this sampling distribution, without understanding sampling distribution, the whole these chapters that we do is difficult. Because we use a sampling distribution, the sampling distribution tells us a little bit some idea. So, I am safe to use one sample because the collection of all these samples would be equal to the population mean. Okay. Now we finish with that. I will upload this one. You don't need to write anything. I mean, if I ask you this question, you would easily calculate. So the answer is not difficult. If I ask you, tell me greater than 33, you could easily calculate. But what does it really mean? Because always there is a claim. And you want to test that claim, either to refute or to get some evidence. In this case, 33 is greater than 30. I am trying to find the probability of 33 or higher. The probability of 33 or higher is very small. So I am saying that if the claim is correct, I shouldn't get this result. This 33, I shouldn't get this result if what this person is saying is really 30 minutes. But I got the result. What does it tell me? The result tells me not to accept the claim. I am concluding he is understating. He is simply putting 30 so that he would sell more pizzas, but in actual term, maybe it is 32 minutes or 33 minutes. So let's go to the other sampling distribution of the proportion very quickly. Sampling proportion, we did this one, x divided by n. It is in your lecture, no, there is nothing new. So x has a binomial distribution, and if it is a binomial distribution, we know the mean. The mean would be NP, and this one would be NPQ. So this is the original. I want to take to the proportion. I have to divide this x by n, because this is x divided by n. So everything will be divided by n. Mu is NP, and sigma is square root of NPQ. So I divided each by n, and finally, I end up with this formula. So this is also the sampling proportion. So the sampling distribution for the proportion. The central limit theorem, what does it say? In the previous case, if the sample size is 30 or above, don't worry about the distribution of the population. Here we are saying if it is NP greater than 5. In some books you will find 10, but let us say NP greater than 5, NQ greater than 5. Don't worry about the population, whether it is normally distributed or not. If the population is normally distributed, any sample size is fine. If the population is not normally distributed, this sample size. So I try to differentiate between binomial and proportion. So this is also in your lecture note. If you take this example, out of 10 voters, 7 prefer candidate A, 3 prefer candidate B. So in a binomial, you would say 7 and 3. In a proportion, you would say 70% and 30%. So that is the difference. In the binomial, it is a frequency. You count the numbers. Like you flip a coin 10 times, 5 head, 5 tail. But in a proportion, you would say 50% head, 50%. So it is an example. The manufacturer of aspirin claims that the proportion of headache sufferers who obtain relief from 2 aspirins is 53%. That is the claim. What is the probability that in a random sample of 400 headache sufferers, less than 50% obtain relief from 2 aspirins? 50. So the question is asking less than 50. This is information given. P 0.53, the claim. The Q 0.47, sample size 400. The question is asking what is P hat or P cone less than 0.50. We apply the formula P hat minus P divided the square root of PQ divided by N. Let us apply that formula. So the same thing you see, P hat scale, Z scale. I calculated 0.50, 0.53 minus 120. The probability is 11.51. Now, my question is that, what do you say about the claim? Do you refute the claim or do you accept the claim? What do you say based on what I said in the previous slide? In the previous slide, I said I refute the claim. Why do I refute the claim? Because the probability is almost less than 1%, very small. It is unlikely. Here, is it likely? 11%? 11% is fine. I mean, anything less than 5%, you would say that it is unlikely, so you refute the claim. In this case, because it is 11%, more than 5%, we will talk about this 5%, 1%, in lecture 3 and lecture 4. We will talk more about that. But given that 11% is a little bit higher, still you could accept the claim. You would say that, oh, probably what he is saying is correct. But in the previous slide, because you get 0.0018, it is really unlikely. It is unlikely to occur. But it occurs. When I take a sample, I got 33. And what do you conclude? My conclusion would be, I refute. I don't accept the claim. He is really understating. He is not telling me the truth. But in the other case, because we got 11, so I'm trying to explain why do we need. Because just simply calculating and giving me the answer is easy. But why do we use? Because the population mean, we don't know. The population standard deviation is given. Population mean is not known. So how do we apply a sample to say something about the population? Here, we are using a sample to say something about the population. And when we want to say something about the population, we depend on the sampling distribution concept. The sampling distribution concept is this one. So the mean of all possible sample means would be equal to the population mean. So that would help me to depend on a sample and talk about the population. This idea helps me to take a sample and to infer or to conclude about the population mean. So could you please go to your Blackboard, lecture 2, learning resources, lecture 2 revision questions. I don't think we have much time, but even if you don't open, let us do it together, because I spent almost half an hour explaining. Okay, let's go. You don't need to open, probably. We will do it together. Okay. When sampling without replacement, finite. Finite without replacement. First of all, when I say finite, what are the distributions that comes to your mind? One is binomial. The other one, Some person is finite. It could be uncountable. The number of customers coming within 1 hour, you count them, but it could be infinite, yeah? So which one do you think this one? Without replacement. You don't replace. What does it mean if you don't replace? P and the Q would be the same or different? What do you think about P and the Q without replacement? You have 3 balls, you take one, you put aside. And again, you take another ball. Do you think the probability would remain the same? It would change. So which one do you think among those which we covered that resembles this one? Yeah, D, hypergeometric distribution. Good. The number of people arriving to a movie theater in a 30-minute time period, which one is that? This is Poisson, because in a given period of time, counting, you count, it is about people counting 1, 2, but in a given period of time, this is Poisson. Let's go to the third. If the outcome of a discrete random variable follow a Poisson distribution, then in a Poisson I said something, because these things maybe you need to go back to your lecture note and try to understand. I think I emphasized when I talk about Poisson last time. The mean equals the variance. So the mean would be equal to the variance. If you go to your lecture note, you will find it under Poisson. Mean equals. These kind of things could come in your true-false questions. So the mean equals the variance, not mean equals standard deviation. Median, we didn't mention median at all. So you have to exclude A and D. You could exclude because we didn't talk about median. At least you would be B and C because we were talking about mean, mu. Students arriving at a local bar and restaurant according to an approximate Poisson process at a mean rate of 30 students per hour. 30 students per hour. What is the probability that the bouncer, the one who is keeping in the front of the bar and restaurant, has to wait more than 3 minutes to card the next student? What type of equation is that? Poisson. Any other? What type of equation is that? The question is, wait, what is time? Time is Poisson? Yeah. But binomial is something that you count. Which one do you think this one? Which? This is exponential. Because the question, the lambda could be the same. Lambda, this lambda we have in Poisson, lambda we have in exponential. The meaning is the same. So it is a little bit confusing. But whenever it is time, you remember in my lecture note, exponential is also about time. So because 3 minutes, it couldn't be counting. It is a continuous variable. So it's not something like number of customers flipping a coin or something that you would count. So it is about exponential. Now, what is the first thing that you have to do? Please, in your exam, also do the same thing. Information given per hour. Here, minutes. So you have to convert. So lambda events per unit of time, 30 students per hour. If it is 30 students per hour, then 0.5 per minute. If there are 30 per 1 hour, per 60 minutes, then it will be 0.5 per minute. 30 divided by 60. So I changed everything to a minute. The information that I got is hour, but the question is minute. So I changed this one to a minute. Would it be possible to do it the other way? You change this one to hour? Yes, it is possible. Either you keep this one, you change this one into minutes, or you keep this one and change this one into, or change this one into hours. So you could do both ways. So the first thing, please, when I give you information hour, but my question is in minutes, you have to convert because your lambda would be different. So the question is more than. If you want to do more than, you have to apply 1 minus this one. 1 minus this value. Minus lambda, 0.5. This is A is the question 3. Now, it's possible to do it, so you could do it simply 2.7 lambda times A. Again, it is possible that you convert. So what I'm doing now, instead of converting this one, I convert this one into hours. I convert this one. 3 minutes minus 0.05 hours. 3 minutes minus 0.05 hours. So I could still use this 30. I could still use this 30 because I changed the question into hour. So, greater than 0.05. Instead of talking about 3 minutes, I am now talking 0.05, but still I could use this 30. It is possible to use 30. Is it clear? So please, in your exam, the given information and the question must, if I give you in hours, my question is in minutes, please convert it first. So the first one is just simply, I convert this one. The second option, I convert this one and keep 30. You don't need to write because you will find it at 12 once we finish the lecture. Okay, let's go to the other. Vehicles pass through a junction on a busy road at an average rate of 300 per hour. 300 vehicles per hour. Find the probability that none passes in a given minute. What kind of equation is that? What kind of equation is that? Vehicles pass through a junction. It is about vehicles, yeah? It is all about vehicles, things that you could count. So the question would be about, and it is given 300 per hour. First of all, is it about discrete or it is about continuous? It is about discrete. And then which discrete? Binomial, Poisson, or hypergeometric? This is Poisson. 300 per given, in a given and limited given period of time. So the question is minute. Information given in hour. Information. So if 300 per 60 minutes, then 5 would be per minute. The question is none. So the probability of none. My lambda would be 5. The question is 0. This is 0. 0 factorial would be equal to 1. Yeah. So please try to convert, especially don't miss. I don't know how in my exam. Sometimes it could be confusing, but I might tell in my question, this is exponential distribution. This is Poisson distribution. Maybe that makes life a little bit easy. But try to understand whether it is a discrete or a continuous. If it is a discrete, ask yourself binomial, hypergeometric, Poisson. If it is continuous, ask yourself uniform, exponential, normal. So there is nothing out of this. Okay, last one. Assume you are taking a test consisting of 60 true-false questions. 60 true-false questions. You are completely unprepared. Yes, this is an example. You will be prepared, no worry. You are completely unprepared, so you make a random guess for each question. But the passing grade is 70% is the passing grade. Use the normal approximation to the binomial. The question is binomial because true, false is binomial. But use the normal approximation that you would pass. So the first thing that it should come to your mind, what is the pass rate? 70% is the pass rate. How many you have to get out of 60 minimum in order to pass, in order to get 70%? 40? 42. You need to get 42. There are a number of things that we need to do when we apply the normal approximation. Please, when I ask you normal approximation, please follow the normal approximation. If you answer the question using the binomial distribution, then you are losing half of the mark because you are not following the instruction. Solution. First calculate NP. N is 60. The probability would be 0.5 because true false. True false has the same like head and tail. 0.50. Then sigma, 3.87. So we have this information. The next step would be greater than or equal to 40 to 70% passing means at least you have to get 42 out of 60. Now this is the formula. But keep in mind, we need, why we reduce this one, 42.5? Why do I write 41.5? Why? Continuity correction. The question is binomial. We are using normal approximation. The continuity correction. If it is greater than 42, it has to be 41.5. The rest, we already calculated 30, 3.87. The question is asking greater or equal. I calculated 0.0. Okay, let's talk today's lecture. Today's lecture, again, we don't know the population mean. But using the sample, we could at least say that the population would be somewhere. The population would be somewhere between two intervals. At least we could guess. In the previous example that I gave you, whether you refute the claim or you accept the claim. Now, let us say, okay, let me try to guess where the population mean would be using my sample. That is what we call confidence interval. So we did all these things. The thing that when we are using X bar, P hat, it is only a single value. It is one value. I say the sample mean is 10. The sample proportion is 50%. It is a single value. It is a single value. It is unbiased. Yes, it is unbiased. The X bar, the P hat, they are unbiased. What is unbiased means? Unbiased means the mean of all possible sample means equal the population mean. That makes it unbiased. But it is a point estimate. And you don't trust a point estimate. You take one sample. These are the same students. I take a sample 160, a sample 162, 165, 167. I shouldn't simply trust one because it could be up and down. Let's say the population, the age of all students in Econ 27300 is 25. If I take a sample, maybe I get 27, maybe I get 22, maybe I get 24. So I shouldn't simply trust only one because it could vary depending on the sample I take, even if the sample size is the same and I did it randomly. So it is a single value. There is a lot of sampling variability. The age, 22, 24, 27, there is a lot of variability. This variability must be taken into account. By using confidence interval, we can estimate the range of value for the population mean or for the population proportion. So confidence interval gives an estimated range. I don't know the population mean, I don't know the population proportion, but I could guess somehow where it is. The unknown population mean or population proportion. This is the example. You see, when I take a sample, this might be small. This is big sample size. Sample mean is bigger, sample mean is small. There is a lot of variability. If you take all the same sample size randomly, there is a lot of variability. So I shouldn't simply trust one. So I have to take certain things into account when I make my calculation. So constructing and interpreting confidence interval, okay? This is the point estimate. The sample mean is point estimate. Sample proportion is point estimate. Sample variance is point estimate. So all these things are point estimate. But what I am trying to do is that confidence interval for the mean, confidence interval for the proportion. That is what we are going to do today. We do confidence interval for the population mean, which is unknown. We want to do confidence interval for the population proportion, which is unknown. That is what we are going to do. As I told you, the point estimate is a good indication because the mean of all sample means would be equal to the population mean. It is a good indicator, but there is a lot of sampling variability. My sample mean is different from your sample mean, from other students' sample mean. There is a lot of variability. Varies from sample to sample, that is what we explained. So this variation must be taken into account. And then taking that into account, what does it mean? You see, in every poll, for instance, there is a political, election. Then the journalists would say that, oh, this year, Democrats will win by 5% plus or minus. Why do they say plus or minus? Because they are depending on sample. There is a lot of variability. So they take into account that variability. If that variability, if for instance I say to you, the age of students would be 25 plus or minus 30. You see that plus or and minus must be small. You shouldn't put it very huge. So if I say, for instance, the population age of students, I don't know, but I could say that it could be 25 plus or minus 3. Some of them, they could be very young. Some of them could be a little bit older than 25. So the variability, I take into account that variability. So this is how we measure the confidence interval. Usually, a 95 confidence interval, a 90% confidence interval, that's what we would say. 95 confidence interval, 90% confidence interval, whatever, 80% confidence interval. You see, this is a normal distribution, 90% confidence interval. So the population mean would be 95% of the cases would be somewhere here. If you make it 99%, you are saying in 99 of the cases, the population mean would be in this interval. But 1%, it could be outside. So, what does 95% confidence interval mean? 95% confidence interval means if all possible samples of the sample size n are taken and their sample means are computed, 95% of the intervals include the true population mean. The true population mean means simply population mean. Somewhere within the interval. And only 5% of them, they don't. So when we calculate, this is the formula that we have to apply. What is this formula tells us? This is the point estimate. What is the point estimate? It could be X bar, sample mean, or sample proportion. This, why do you make plus or minus this value? Because of? Why do we make plus or minus this value? Because of the variability. Because we take only one sample. But we know that there is a lot of variability. There is a lot of variability. So we take into account that variability. So always point estimate, X bar or P hat, plus or minus critical value. This is what I find from the table. And standard error must be estimated. The whole, this one, we call it margin of error. Point estimate plus or minus margin of error or sampling error. So point estimate plus or minus sampling error, because when we take a sample, there are a number of different results. So that differences must be taken into account. Sometimes in some books you will find margin of error or sampling error. So point estimate plus or minus margin of error. This one you will find from the table. This one you will calculate it, or it would be given. Point estimate is X bar, the mean of the sample, or the proportion of the sample. So let us go to this example. What does it mean 95% confidence interval? Keep in mind, we don't know the population mean, but we're assuming that it is here. If I make a 95% confidence interval out of 20, 95 confidence interval means in 19 cases, the population mean would be somewhere. You see, here, population is there. Between here and here, the population is still there. Between this and this, the population is still there, the population mean. Between this number to this number, population mean. Only here that the population mean is not included. So, what is good? To make the confidence interval large or small? What about if you make it 90? If you make it 90, what does it mean? How many would be included? Only 18. 2 cases will be outside. So the best would be if you have a very large confidence interval. What does 95 confidence interval in a very simple explanation. 95% I am correct that the population mean would be here. But in 1%, the population mean might not be here. So if you want the population mean to be exactly here, it is better to have 99. 99%, the population mean would be somewhere here. But in 1%, it could be outside. So the more the confidence interval you make, because look this one. In a 95 out of 20 cases, 95%, 19 would be. If you make this one 80%, if it is 80%, 16 would contain population mean. But 4 of them, they wouldn't contain, isn't it? So this is what we are going to do today. So still, lecture 3, we haven't properly started. We just simply introduced it. Population mean. I will do a confidence interval for the population mean, for mu, when population standard deviation is known or when population standard deviation is unknown. If population standard deviation is known, I use Z table. If it is unknown, I use T table. Again, if it is known, I use sigma. If it is unknown, I use the sample standard deviation. Sigma, the population standard deviation. But here, because I don't have, I have to use the sample standard deviation. So there are slightly. When you talk about the proportion, always you apply Z test. Proportion, always Z. Mean, it could be Z test, it could be T test. When you apply Z test, population standard deviation you have, it is known. But when you are doing T, population standard deviation is unknown, so you have to use a sample standard deviation. So let us talk a little bit. So population standard deviation is known. This is known. The population variable is normally distributed. That is fine. If the population is not normally distributed, sample size must be greater or equal to 30 in order to do your confidence interval. If you have a little bit less than 15, but the population is fairly symmetrical, still sample size greater than 15 is fine. That's why in some books you will find, assume n or assume the sample size is 10. Please do this and this. Then finally they will write, assume the population is normally distributed. If your sample size is, let's say, n equal 50, do I need to say to you that the population is normally distributed? No, I don't need, because the sample size is greater than 30, greater or equal. Okay, this is the formula that we applied. What is my aim? My aim is I want to know the confidence interval where the population mean would be somewhere in the middle. So I want to calculate population mean. So I take out this, I rearrange it, it becomes like this. X bar minus, this is what we will find from the table. You see, this Z, what we will find from the table, critical value, and the standard error would be this one. This is the standard error, this is the critical value, but together we call them margin of error or sampling error. Normally, if you want to calculate mu, it must be minus. But conceptually, we know that the population, the sample mean could be sometimes higher than the population mean, sometimes lower than the population mean, isn't it? Let's say the population mean age is 25. If I take a sample, it could be 26. If I take a sample, it could be 23. So it could be plus or minus. Then I put plus or minus. So this is how the confidence interval. And then whatever this alpha is given, it has to be divided by 2. Why do we divide it by 2? Because we are talking about two ways. So the confidence interval is between this number to this number. So there are 2 ways, yeah? The smallest, the highest. So this alpha must be divided by 2. Okay, now, you see, once you take this one from the table, this is, you calculate it, the standard error, this is, it is given, then you would estimate that the population mean would be somehow between these 2 values, because we don't know the population mean. This is 101 minus alpha percentage. If alpha is 5, then it will be 95%. If alpha is 10, then it is 90%. If alpha is 2, then it is 98%. So if I give you alpha, then it means 95 confidence interval. If I give you alpha 10, then the confidence interval is 90%. If I give you alpha 1, then the confidence interval is 99%. So in the above formula, the value of Z needed for the constructing a confidence interval is called the critical value. This is the critical value for the distribution. For a 95% confidence interval, the value of alpha is 5%. So the same thing, point estimate, plus or minus, the critical value times the standard error. So this is fine, I mean, it is just reading, but let us go mainly. Now, this is the 95% confidence interval. 95% confidence interval, 2.5% to the right remaining, 2.5% in the left remaining. If 95% confidence interval, what is alpha? For a 95% confidence interval, alpha is 5. 2.5 on the right-hand side, 2.5 on the left-hand side. Now, if I ask you to find from the table 1.96, which value are you going to check? You remember, the Z table always gives us to the left. If I ask you, please give me this number, which probability do you have to search? If you want to find this one, this plus this plus this, isn't it? So you have to find for 0.975. But if you want to tell me this one, which probability do you have to look? 0.025, eh? Because alpha is divided by 2, yeah? So always, which one is the easiest for you? This is the easiest. Here 0.025, you go to the table, you find it, then plug the numbers. So this is simply a theoretical explanation. If you want to find this one, you have to find probability of this, which means 975. If you want this number, it is 0.025 would be enough. So I go to the table, 1.96, 0.975. 0.975, it gives me, because it is always to the left in our textbook. Now that is also what I will give you in your exam, so it is good to know how to read from the table. Or you could find 0.025, which gives you minus 1.96. Minus 1.96, 0.025. But in general, always keep in your mind, if I say 95%, automatically 1.96 minus 1.96. If I say 90%, so usually in exam or in anything you will find 95% confidence, 90% confidence, 99% confidence. So sometimes you could even memorize without, when we are talking about confidence interval. 90% confidence interval, 10%, 5% to the right, 5% to the left, 1.645 minus 1.645. 95%, I'm talking this is about confidence interval. 95%, 1.96 to minus 1.96. 99%, 2.575 minus 2.575. So sometimes students would memorize these things instead of every time you go to the table. Okay, now, if I want to know alpha 0.20, if alpha is 0.20, I have to the right 10%, to the left 10%. Which one do you prefer looking in the table? Left, which is 10%. So I want to find this left, minus 1.28, the 10%. So I go to the 10%, then minus 1.28, minus 1.28. Once I find the minus, I put the plus also in the other side. So this is when population standard deviation is known. We are doing about the mean, population mean, but population standard deviation is known. Okay, example. A random sample of 81 items produces a sample mean of 47. Sample mean 47 is a point estimate. So point estimate plus or minus critical value times standard error. The population standard deviation is 5.8. Construct a 90% confidence interval to estimate the population mean. For a 90% confidence interval, alpha is 10%, 5% here, 5% there. Which one is easy for you to find from the table? Either you have to find the 5% to the left or 90 plus 5. If you want this one, 90 plus 5, 95. So you could use that one. And then I found minus 1.645, 1.645. The rest is simply a matter of calculation. We know the point estimate 47 plus or minus this value times critical value times critical value times standard error is sigma divided by the square root of n. Okay, let us do that. 1.645 sigma given 5.89, my sample size. Do I need that the population normally distribution information? Do I need information what the population, whether the population is normally distributed or not? Because our sample size is greater than 30. So we would say finally, we don't know the population mean, but we could guess using our sample and doing a little bit of technical things, which means the sampling error. We know the sample mean, plus or minus the sampling error or the margin of error. We could say that the population mean would be somewhere between these two numbers. We still don't know, but at least that is some information. So how do I know? Minus 1.645, either 5% or 95%. Why do I put 1.645? You will see it. 1.645. Because for 5%, 95% confidence interval, the critical value is 1 point. For 95% confidence interval, the critical value is 1 point. 1.96. But here I have 3 digits. You see? 3. But here also 3 digits. Why this is only 2, whereas here 3? So let us see that one to that question. For this question, I am searching 5%. When I search for 5, let's say maybe I am searching first the 95%. When I search the 95%, 95% is exactly in the middle. It is exactly in the middle. This is 94, 95, 95, 05. 5 less, 5 more. So it is exactly in the middle. If it is not exactly in the middle, you take the nearest. But this value, 95, 0.95, is between these two numbers, exactly in the middle. So it is better to take the average, which means 1.645. It is between 1.64, 1.65, in between 1.64, 1.65, which means it is in the middle. That's why I have 3 digits. Because it is exactly in the middle. If it is not exactly in the middle, what would you do? You take the nearest. You take always the nearest. For instance, if you are searching for 0.9504, then you will take this one. 9504 is close to this one. But 95 is exactly in the middle, so 1.645. The same thing when you do the other way, the same thing. 5% is between 0505 and 0495, exactly in the middle. So I take minus 1.645. So it is between 1.64 and 1.65. So that's the reason. Now, maybe let us have a break of, 7 minutes, and we will start with when the population standard deviation is not given or unknown, we have to apply t-test. In a t-test, it would be a little bit different how to read. So let us have a break of 7 minutes break, and then we'll continue. Let us continue. When we talk about this 95% confidence interval, because the whole idea, we don't know the population mean, but you want to estimate where the population mean would be. The whole exercise of today is we don't know the population mean, but we want to guess where the population mean would be using a confidence interval. Now, if you go to this concept, what does this concept tells you? If you construct a 95% confidence interval, then 95% of the intervals include the true population mean. But somewhere, only 5% they don't include. So, now, theoretically, could it be possible that your sample could be this one? Because you don't take many samples. If all possible samples of the sample size n are taken and their sample mean are computed, in 95% of the cases, the population mean would be somewhere in that interval. But in 5% of the cases, it could be outside. Could it be possible the sample that you are using could be this one? Yes, it could be this one. So sometimes it doesn't give you the whole picture because it is possible that my sample, but overall, the probability that my sample could be one of these would be high. By chance, my sample could be this one. So whatever I calculated, it doesn't give a good result. So 95%, so what is the option? You increase 99%. In a 99%, you have a lot of opportunity. So always increasing the confidence, but in reality, this could happen. Your sample could be this one. Your sample could be this one. Your sample could also be this one. Because the theoretical concept is saying that if all possible samples of the same size are taken and their confidence interval is calculated, 95% of the interval would contain the population mean, but 5% they don't include. Your sample could be one of those 5%, but the probability is less because 95 is higher. Another concept that you might ask yourself, which a little bit difficult to understand, why we don't know the population mean when we know the population standard deviation? You could ask that question. So it's a little bit tricky also. Why we don't know the population mean, but at the same time we are saying we know the population standard deviation. If we know the population standard deviation, we should know also the population mean. So it is a little bit, but that is the way it is. So let's go to the T. Now, if the population standard deviation is not given, we don't apply Z. Instead, we have to apply T. What does it mean? This would be changed to T. Everything the same, this has to be T. And the value of this critical value has to be obtained from the T table. When we obtain from the T table, then we have to do, how many samples we are taking in this example? How many samples? No, that is sample size, but how many samples? We take one sample. You ask 81 people, yeah? You get a mean of 47. So you take one sample, you ask 81. So we have one sample in this question. So always to find the critical value in a T table, n minus 1 degrees of freedom. Why? Because we are taking one sample. Assume that you take a sample, but that sample has a sample size of 100, sample size of 50, it doesn't matter. But the sample that you are doing, you calculate only one mean. You calculate only this sample mean. So it means 1. We are talking only about sample mean. Huh? Okay, let's go to that. So everything is applying. Instead of sigma, we would take the sample standard deviation. We use the T distribution instead of normal distribution Z. Usually, T approaches Z as sample size increases. When sample size increases, whether you are applying Z or T would be the same. What does it mean? When is T and Z approaches? Z and T approaches when you have a sample size of 120. For instance, 95% confidence interval. The Z value would be 1.96 minus 1.96, isn't it? 95%. If you are using the T table and you have sample size of 120, then it would be the same, 1.96 minus 1.96. So if your sample size is 120 or above, whether it is Z or T, the critical value would be the same. You could see in your T table. So unknown, everything population variable normally distributed. If not, large sample size, 30 or above, the formula would be the same. The only thing here, we have to take into account the degrees of freedom. If you want to find this one, we need n minus 1 degrees of freedom. Sample size minus 1. That is what we call degrees of freedom. Here you don't have sigma, instead you have sample standard deviation, not population standard deviation. The table you will find, so this is the critical value, this is the standard error. Property, very similar to the normal distribution. Both are bell-shaped, but T distribution has more areas in the tail. Because the population standard deviation is unknown, the value of T are more variable than those for Z. Because S is from the sample. You trust more the population standard deviation rather than the sample. Because if I take one sample, the standard deviation could be different from the other sample, from the other sample, from the other sample. So it is more variable. It varies from sample to sample. But as sample size and degrees of freedom increase, which means 120 or more, you could see your table. In your table, 5%, which is 0.025, 120 sample, then 1.96. The same like the Z value. With a sample size of around 120 or more, it would be precise. The critical value would be the same, whether it is Z or T. You see, this is the distribution. This is the standard normal distribution. If you have a degrees of freedom 13, it would approach the normal distribution. If the degrees of freedom 5, it's not looking like this. So the more you have degrees of freedom means n minus 1. So here you have 14 sample size, here you have 6 sample size, n minus 1. What is that one? That one is the x bar. X bar, we are using only sample mean. So that is minus 1. So minus 1. This minus 1 is always because we are taking one sample or because we are calculating x bar, then that is minus 1. Okay, so how do we find? The table in your textbook only gives you the positive value. You remember the Z value gives us minus 1.96 plus 1.96. But the T table only gives us positive value. So once you find the positive value, you put the negative value yourself. The table doesn't give you negative values. So let's say alpha 10%. If alpha is 10%, 5% to the left, 5% to the right. My sample size is 3. If my sample size is 3, n minus 1 is 2. So I go to degrees of freedom 2, 5%, because alpha is 10. Then I find 2.92. I put 2.92 here, minus 2.92. So always please don't forget n minus 1. Alpha divided by 2, the same thing. But n minus 1, don't forget. So let's go to this one. If a random sample of 41 items produces a mean of 128 and a standard deviation of 20.6, sample standard deviation 20.96, what is the 98 confidence interval? 98 confidence interval to the right, how many percent? How many percent to the right? If you have 98 confidence interval, to the right you have 1%, to the left you have 1%. So you have to search 0.01. Instead of this one, you have to search 0.01. And the degrees of freedom is, how many degrees of freedom do we have? 40 degrees of freedom. How do we know that this is, that we use T table instead of Z table? How do we know from the question? How do we know from the question that we apply T test, T critical value? When do we use T critical value? When the population standard deviation is not given. We have only the sample. Sample size, sample mean, sample standard deviation. When we have only S, we automatically know that we have to apply the T critical value. So the degrees of freedom is 40. Alpha is 2. To the right, 1%. To the left, 1%. So 1% because alpha is 2. To the right is 1%. Degrees of freedom 40, 1%. 1%, degrees of freedom 40. I found 2.4233. So plus 2.4243 minus 2.4243. If you go here, continue, 120, then whether it is Z or T, the critical value would remain the same. Another example, a stationery store wants us to estimate the mean retail value of greeting cards that it has in its inventory. A random sample of 100 greeting cards indicate a mean and the standard deviation. This is sample standard deviation, sample mean, sample size 100, 95% confidence interval. You see, if this question is a Z table, what is the confidence, what is the critical value? Now, because this is 100, close to 120, probably it would be not 1.96, but around that area, I would expect. So 95% confidence interval. 2.55, you see, 1.98. If it were Z, 1.96. Now it is 1.98. Because with a sample size of 100, the degrees of freedom is 99. 99 and 120 is not that far. Because if it were 120, then as I told you, it is precise. Whether it is Z, whether it is T, the critical value would be the same. But we have only 100 in this example. N minus 1 is 99. I went to the table. I found in the table, well, I don't know whether I don't have in the table. So I found 1.9842 plus minus, I calculated. Then you could interpret if you want. With 95%, we are 95% confidence that the population mean would be between these two numbers. 95% confidence, but 5% we could make an error. That error comes, this is the margin of error. Whatever you do, that's why, in the political election, they say that 5 plus or minus 2. What does it mean? 5 plus or minus 2 means it could be 3 or it could be 7. 5 plus or minus 2 means it could be 7, it could be 2, somewhere. So 5 plus or minus 2 means that 2 is the margin of error. Why do they put the margin of error? Because they are taking a sample. So the sample variability exists. So you have to take into account that variability. So with 95% confidence, we can conclude that the population mean retail value greeting cards is somewhere between these two values. This one is a little bit of, because you have to calculate the mean, sample mean, you have to calculate the sample standard deviation. Don't forget, when you calculate the sample standard deviation, you have to n minus 1. Why do you make n minus 1? Because the same thing, that sample variability. If it is the population, you would do divided by n capital letter. N capital letter is the population size. N is the sample size. So the whole process is the same. The only thing you need to calculate yourself. In this question, everything is given. But here, you have manually to calculate first. How do you calculate sample standard deviation? For each, 4 minus 5 square, 6 minus 5 square, 3 minus 5 square, then you add it. Then divided by n minus 1, n is 1, 2, 3, 4, 5, 4, then you get. You go to the table, 90% means 10% to the right, 10% to the left, 5% to the right, 5% to the left. How many degrees of freedom do we have? The degrees of freedom would be 1, 2, 3, 4, 5, 6, 5 degrees of freedom, exactly. Okay. the same thing let us do for the proportion. Let us do the same thing for the proportion. Now it is a little bit different. You remember what we did for the mean. This is how we started when we do for the mean. This is where we started when we do for the mean. It started from here. We want to calculate the population mean. Then we add plus because of sampling error, because of the error, margin of error. Now let us do the same thing for P. This would be P, this would be P hat. P hat is the sample proportion, but we want to know where the population proportion would be. Do we apply T or Z? What do we apply, T or Z, critical value? Z. For all proportions, always Z. Okay, let's go to that. So this is the formula. I want to find this calculation, P. But when I try to calculate this P, the same thing like I did in the previous case, when I try to calculate this one, it becomes like this. If I want to know this one, at the same time it is here, it is difficult to calculate. You have unknown here, you have unknown here, isn't it? So it is difficult to calculate. You want to calculate P, population proportion. If you want to calculate this, but where do you find this one again? So what does it mean? Algebra, using algebra, manipulating this formula to estimate P involves solving for P. However, P is in the numerator and the denominator. So it is difficult to calculate because you want P, but at the same time you don't know P. P is numerator, P is the denominator. In that case, it is difficult to calculate. So only for a confidence interval case, only in this case, instead of this, let us change this P and Q to P hat and Q hat. P hat means sample proportion. When you put the hat, it is the sample. So because we have difficulty to calculate this P, we change this one to P hat and Q hat. By doing so, we can easily calculate now. So please only use capital letter here. It was small letter in your lecture note. For this reason, for confident interval purpose only for the confidence purpose interval only, let us put here P hat, Q hat. This is margin of error. This is the point estimate. This is the critical value. This is the standard error. So keep in mind, actually it should be written P and Q, but it is difficult. You want to calculate P, again you don't know P. How do you calculate then? So that's why only for the confidence interval purpose, let us put P hat and Q hat. Now it is fine. If it is normally distributed, that's fine. If not, NP greater than 5, NQ greater than 5 still satisfies. Let's go to this question. A student of 87 randomly selected companies with a telemarketing operation reveals 39% companies telemarketing to assist, so 39% point estimate. Because it is 95%, 2.5 to the right, 2.5 to the left, the critical value is plus or minus 1.96. Then we calculate, this is from the sample, 39%. Q would be the rest, 61. This is the sample size. So we are 95% confident that it would be between 29% and 49%. We don't know the population proportion, but we could estimate somehow the population proportion using the point estimate plus minus the margin of error. Now, let's go to another concept. Look, what did we do now? Let's say the population mean. We calculate a population mean using confidence interval, yeah? Let's say now we did here the age of students. These are the whole students enrolled in Econ 7300. Now finally, once we do the calculation, we take a sample, we calculate, then we say the age of a student is between 20 and 40. Does it give a lot of information? It doesn't give you a lot of information. Because 20 to 40, or let's say the age of a student is between 30 plus or minus 15. 30 plus or, so the oldest would be 45, the youngest would be 15. I mean, technically, postgraduate 15 you wouldn't find. But let us say between 50 and 30. Does it give some sense? If I tell you, for instance, my age is between 30 to 60, do you get some information? It doesn't tell you much. So, because of that, we have developed confidence interval for population parameters on the basis of the information contained in a given sample. Following such a process, we may believe that the resulting confidence interval is too wide. You would say, if I tell you my age is between 30 and 60, you would say that, oh, this teacher didn't give us nothing. He didn't tell us anything because 30 to 60 is too huge. So you need to think, maybe the sample size is not correct. Because look, in all this formula, the sample size matters. If the sample size is higher, very large sample size, what do you think about the confidence interval? If the sample size is large, the confidence interval would go narrow or wide? It would narrow. So narrowing is good, isn't it? So instead of telling you 30 to 60, maybe narrowing 30 to 50. You would say, oh, now it's fine. So let us now calculate the sample size. Because the confidence interval, it is too large, it didn't give me any information. Maybe if I know this one exactly, that would help me to narrow my confidence interval. So if you are thinking that way, we may believe that the resulting confidence interval is too wide, reflecting undesirable amount of uncertainty. My age, 30 to 60, uncertainty about the parameter being estimated. In some circumstances, we may be able to fix in advance the width of the confidence interval, choosing a sample size big enough. In all the examples that we did, big sample size matters. If the sample size is large, the confidence interval is narrow, the information is useful. Instead of saying between 3 to 6, you might say maybe between 4 and 5. So let us, how do we know how much or how many sample size we need? How do we know? So we have to follow the formula. We still stick with what we have been doing. Okay, let's go to that. Maybe this is, you can read that one. This is the formula that we have. If you remember, with regard to population mean. This is the formula that we applied. Now, I want to calculate this. I want to calculate this because I want to know what is the required sample size. Before doing the confidence interval, in the previous examples, we simply do the confidence interval, taking a sample. But now first, I want to know what is the required sample size. Once I know the required sample size, definitely that would help me to narrow the confidence interval and I would get some meaning. So definitely this information that I put, you need the level of precision. The confidence interval is alpha, we know this one. This is about variability. Variability means that what do you think about the sample size? For instance, if I have many students, different students are from different country. And let's say the other group, all of them from one country. We have two classes. One class, all students from one country. In another class, all students from different country. Where do you take more sample? The more sample should be from different? Yes. But for the same country, maybe you need small sample size would be enough. So the variability. If people are homogeneous, sample size less is okay. If people are very heterogeneous, then more sample size. The precision means the plus or minus. The precision is the margin of error. If I say 5 plus or minus 2, 5, or if I say 5 plus or minus 10, the precision is plus minus 2 rather than plus minus 10. So the precision means when the margin of error is narrow. Okay, so my idea, maybe let me give you one information here. Let us assume this is 7 plus or minus 2 would give us 7 minus 2, 5, 7 plus 2, 9. The confidence interval is between 5 and 9. In the middle, what is the middle? What is the average between 5 and 9? What is the average? If you add 5 plus 9, divide by 2. 7. So the average of this one would be the point estimate. So the point estimate is the average of this. So I could ask you this kind of question in a true false or something. So if you take the average of the smallest, the highest, divided by 2, it would be equal to the point estimate. Another thing, what is the width of the interval? What is the width between 5 and 9? 4. Half of 4 would be 2. So it would be the margin of error. So the width of the interval divided by 2 is the margin of error. The width of the interval divided by 2 is the interval. Half of the width of the interval is the margin of error. So always keep in mind, between 5 and 9, the width is the interval is 4. The difference, half of that 4 would be the margin of error. Another concept, the average between the two would be equal to the point estimate. But the main thing is now how to calculate n. Let us calculate n. So, let us call the whole these things E. Let us call the whole these things, what is this red? Circle in red, what do we call it? Point estimate, critical value times standard error. What is this red? Margin of error. Let us call it E. So, x bar plus or minus this E. Let us put this one is the margin of error. The whole this is margin of error. Let us square it so that this n would be out of the square root. And now let me try to find n. N times this one would be, and then n would be something like this. Because you see, if you see this formula, sorry to take you back, this doesn't play any role. What plays role is this one. The effect of the sample size changes the whole these things, isn't it? You could have 5, but what is added plus or minus is the most important, isn't it? Because this is not important. You could have any number. What is important is what are you adding or what are you subtracting. And that n is the one that we want to find. The margin of error, I square it. So z square, sigma square. When I square this one, n remains. So n times this would be this one. And then at the end, it looks like this. So always my sample size, the required sample size, could be greater or equal to this number. It has to be an integer. If you find 12.5, you have to call it 13. If you find 12.1, you have to say 13. Anything, you don't go to 12.1. If it is 12.1, don't go 12. Always the next. So it says here, the higher integer. So greater or equal to this value. If you calculate here 12.1, it would be 13. If you calculate 12.9, it would be 13. Always, this is how to calculate the required sample size from the margin of error. We take the margin of error, we calculate for n. Because in the previous cases, we didn't care about n. We just simply do the confidence interval. But we may feel that the confidence interval is too large. It doesn't give me any information about the population mean or population proportion. So I am asking back, let me first decide what the required sample size is. So using this information, it is simple. You plug the numbers and then you calculate. So for the first E5, this is 40, 99%. If it is 99%, 2.575, then you calculate. The required sample size, 425. The second question, 10, 40, 95%, 1.96. This is 1.96, always a two-tail. Don't forget, it is like a two-tail, we think. 95, 1.96. Then the required sample size, 62. Now there are two concepts that we need to apply, so it is pretty much easy because we come from this, we call it margin of error. So we are concentrating on this one, margin of error or sampling error, to develop an equation for determining the appropriate sample size needed when constructing confidence interval. Estimate, recall the formula, then, because this is not that much important. This is the most important. That changes the whole process. Because if this is greater, then this would be narrower, irrespective of this. Okay. Now let's go to the unknown. What do you do in the case of unknown? Now let us assume this is known. Population standard deviation is known. That's why we are applying this, population standard deviation. Now, you want to know the required sample size. You want to know the required sample size. Before you go to a survey, before you ask people, you want to know the required sample size. Now, you don't have the population standard deviation. What do you do? What do you do if you don't have the population standard deviation? Huh? But if you have, because you said sample standard deviation, yes? But if you have sample standard deviation, it means you have already sample size. I want to know my n. Is it clear, the idea? If you have already sample standard deviation, then it means that you have already n, isn't it? So what do we do in that case? Who can tell me? Huh? What? What? Yeah. You take what? Take data and calculate. Yeah. I mean, he is close. So because if you take the whole, we take a pilot. Instead of asking 40 people, you ask only 10 people. From that 10 people, you pick that S. So we call it a pilot study. So you make a pilot study, a short sample you take. For instance, if you are going to ask all unemployed people in Brisbane, your pilot study would be only you go somewhere, West End, you ask those people. So that is a pilot study. Before you do the big study, you do a pilot. So we have to apply a pilot study. Select a pilot sample. Why do we do that? In order to get that S. Once we get S, the rest is the same thing. The calculation would be the same. So, to do the population standard deviation should be approximate, okay? Then you do the pilot. So you make a study, but it's not a huge study. Because if you do a huge study, you already know the N. But if we want to know N, but population standard deviation is not given, we do a pilot study. So using that pilot study, we calculate. So there is no example, which is very simple because one thing that I need to remind you, this Z always remains. In the required sample size, you always apply Z. The required sample size, it's always Z. The required sample size is always Z. Okay, now let's go to the other one. This is, you see now, we don't have P hat, Q hat. Why? If you remember, P hat, Q hat, I mentioned here, I said here, only, we do this one, P hat, Q hat, only for the purpose of confidence interval. Otherwise, we leave as it is. We leave as it is. So I left it as it is. Then I try square it because I want to find n times this margin of error squared, and then finally I end up with this. I mean, there is nothing new here. I just simply, so it must be greater or equal. Now the question, where do we get this P and Q? How do we get this P and Q? I want to know my sample size, but we don't know P and Q because P and Q is unknown. The population proportion, I don't know. And Q also the population of the opposite of the other one, I don't know. So I have three methods. This is the formula, greater or equal. How do I calculate about my sample size required when I don't know about P and Q? Three options you have, three options. One option, yes, you don't have P and Q, but you know long time ago there is some information, past information about P, for instance. What could it be, for instance? What is the number of the proportion of people unemployed in Queensland? We don't know that information, but maybe there was a research 10 years ago that tells us that information. So I still use that information. Past information. The second one, this P is unknown. Researchers use P 0.5. Why do I use 0.5? The first one is clear. You don't have P. You don't know the population proportion for today. But you might rely if there is information from last year or before last year or 5 years ago. That is clear. Let's go to the second point. Why do I use 0.5? Why not 0.4? Exactly. Yeah, to increase your sample size. So if P is 0.5, what is Q? Okay, 0.5 times 0.5 is 0.25. What about if P is 0.1? Then Q is 0.9. It's still less than 0.25. So we are taking P times Q, that gives us maximum. The maximum, because if we make this one maximum, this N would be also higher. So we are taking 0.5, which is the highest that we could put, because 0.5 times 0.5 is 0.25. If we put P 0.9, Q would be 0.1. When you multiply it, then it would be 0.09. So that is the second option. The third option, we take also the same thing, pilot study. We ask few people, then instead of P, we will have P hat. So the third option that we have, I don't have this one, I don't want to use this one. The third option that I have, okay, I will ask only few people, then based on that, I will apply P hat as if it is equal to P. Okay. Now, the first one, who can tell me what is the disadvantage of the first one? What is the disadvantage of this? What do you think if I use this one, what is the disadvantage? For instance, I am calculating now, but the P is 10 years ago. So what is the disadvantage of that? Because it is an old data, it doesn't give me accurate result. What is the disadvantage of this one? Too bigger sample size. If I put 0.5, 0.5, I am making my N is too large. Sometimes larger than one it is required. And larger, what does larger sample size mean then? It is costly because you have to ask people to, when you are interviewing, you have to, all these things, it is costly. So sometimes you might have data more than it is really required. The third one, the disadvantage is we are not really using P. What we are using is P hat. So that's by itself also, it is a sample proportion. So a reasonable approach, it is reasonable to use, but how often such data available? First, you wouldn't find, and might P have changed enough to make it a questionable assumption. If 10 years ago, the proportion of unemployed was 10%, you shouldn't use that one for this year. This method is conservative. Conservative because it gives high N and ensures the desired precision. It is therefore a sound choice and is often used. However, the sample may end up being larger than necessary because P and Q would be higher. This method is appropriate if P is believed to be differ greatly from 0.5, as is often the case. So if you don't trust this one, the other option that you have is you take a preliminary sample. So these are this here, for instance, we apply method 2 because P and Q is not given. I don't have P. I don't have sample, I don't have pilot study, I don't have historical data. The only option I have is simply to use method 2. In this question, method 2 would apply. So always Z, the same thing. This is the required sample size is 664, required sample size 271. So what we did today is not huge thing, even if we cover a lot of slides. Confidence interval, population mean, population standard deviation known, confidence interval, population standard deviation unknown, confidence interval for the proportion, and how to calculate the sample size, the required sample size. So we only covered 4 things. So we'll do next week. Once we do next week, the other week we don't have class because there is a preparation tutorial for your mid-semester exam. So for the preparation of your mid-semester, I would prepare extra questions so that you could do those questions with the tutors. Next week we have a quiz. We have quiz 1. So please, don't forget. Thank you.